Is it recording? Yes. Okay. I think we're set here now. Sorry about that. Not sure what the initial problem was, but I think we're set now thanks to my son who came up to my rescue. Sorry about that. So I switched to a tablet today. So that's the challenge. So this way I can write on the notes, but despite numerous attempts at thinking that I had everything set, I think I do now. Okay. So, well, welcome. I'm going to switch a little bit in terms of the mode that I'm doing today. Is that I'm switching, to, like I said, to a tablet. This way I actually should be able to write on the notes, but I'm getting used to things. So I apologize for any problems that we have today, but we should be good. At least I hope. So I just wanted to start the I wanted to start the lecture with just some logistical information. And so I've posted a new syllabus, so it's slightly revised. There are no changes to the grading in the first half of the semester. So the first half of the exam is still worth 20%. The homework is still worth 7.5%, and participation is still worth 10.5. So basically think about that in terms of points, towards 100 points at the end of the semester. I am eliminating exams 2 and 3. Hopefully this will help relieve some of the stress on all of us. Homeworks for the second half of the semester will be worth 20%. So I'm really expecting that through the homework, you'll hopefully master the material. The project is worth 42%, so I've increased that some. There's an interim report and then a proposal and the poster. You'll prepare the poster, but we won't be presenting the posters this year. But by preparing the posters, we can actually put posters in the hallway. So the top 10 will get their posters printed. I will print them once life is resumed to normal, and then I will post them in the hallway. And then participation is worth 10.5%. That was a little bit more than it was previously. Just a reminder in terms of due dates. Wednesday, there are 2 homeworks due, one on greenhouse gases and then the other on air pollution regs. The air pollution reg homework is pretty much all fill in the blank, short answer type, multiple choice. So it shouldn't take you very long to do that. And then any other home deadlines I sent in a email message this weekend. A number of you have asked about the corona cases or what's happening with COVID-19 corona. And I just want to give you a little bit of information. This is a plot that I saw on the weekend. I actually did some research to check the source of the data beyond the article that it was published in. And basically the Korean data is from CDC Korea, and the Italian data is from the Italian government. But one of the things that I really want to show you that I think is critical for you to think about is this information right there. And difference between Korea and Italy, South Korea and Italy, is that South Korea has been testing very widely. Doesn't matter if someone is potentially exposed, they're testing whether or not they're symptomatic or asymptomatic, and Italy is only testing those individuals that are symptomatic. And one of the things you see from the data from South Korea is that there's very significant number of individuals that are in the 20 to 29-year-old range that are testing positive for COVID-19. So many of these individuals are asymptomatic. So you can see from the Italian case that only about 3.5% of the cases are symptomatic in that range, but yet there's a significant percentage of individuals in the 20 to 29-year-old range that are testing COVID positive. So one of the things I want you to think about, kind of as you proceed and have contact with various individuals, that you may be asymptomatic, but you may be potentially a carrier of COVID-19. Potentially, you can see when you get older, it tends to be, if you're if you have the virus, then you're likely to be symptomatic. So that's something just to think about as you kind of move forward. I do have one question about posting tablet notes. I will post lectures as normal. Yeah, I'd be happy to save the slides and then post my notes with the comments with any writing online. So yes, I will do that. I'm going to try. All this is new. It's all new software to me. So please bear with me kind of as we move forward over the next few days as I get used to the software, the new software. So let's move on to the next unit. So the next unit we're really looking at is we're starting to look really at transport. So how do these gases, these various different air pollutants, how do they move in the environment? And in order to do that, we need to know something about meteorology. I've shortened the lecture from what I've done in the past just because of the situation. But I want to give you at least some basics understanding of air movement, and then we can actually move into looking at air transport or pollutant transport and doing some modeling. So one of the things to think about, and we looked at this slide here showing we have Chernobyl. So it was in 1986, that was the radioactive fallout occurred from Chernobyl. And what you see is a significant movement of the radioactive fallout across the globe. And you can actually see it all the way where it was actually tracked all the way through to the United States. So the question is why? How did that happen? I'm not going to play the video. It's actually in the link. So if you look at the PowerPoints, you can watch the video. But again, you see this turbulent, you can kind of see it here, this turbulent behavior, the movement of air in various different directions. So how does it happen? Why does it happen? Now, all of this air movement controls the dispersion of pollutants. So we really want to think about, how does this happen? So this air movement is the predominant mechanism by which pollutants move through in the environment. What causes that? Normally I wait for an answer, but so the major thing, okay, again, is these air movements. What causes air movements? What's causing the air movements is a change in temperature. And that change in temperature causes a change in pressure. So what happens is air is going to move from from high pressure to low pressure. Just like kind of think about water moves from high elevation to low elevation. And as that air moves, it's going to take with it, or we can talk about advection. It's going to take with it these pollutants. Now, we can also have velocity fluctuations, and I apologize, I'm getting used to the tablet. But we have these turbulent velocity fluctuations. In many respects, that's the result of surfaces. So you've got irregular surfaces. You can kind of think about that. It may just be close to the Earth's surface, trees, buildings, etc. It can be much larger, mountains. Okay, those structures result in friction. That friction results in turbulence, and that turbulence then disperses these pollutants in all directions. And then the last is simply diffusion. So if you have very stagnant air, then, and kind of think about that, if you are in a room, someone is cooking something on the stove, and you're maybe several rooms over, eventually you start smelling what they're cooking on the stove. Hopefully it's a wonderful smell. And they're doing a great job cooking, and you can smell it over, and it takes time. Why? Because those chemicals that cause the odor, okay, that cause the scent from the cooking are diffusing. In many cases, especially if air is stagnant, they're diffusing from high concentration to low concentration. All of these factors affect how these pollutants move in the environment. The basic element of the circulation in the atmosphere is wind. I'm not going to spend a lot of time talking about wind. Normally I would talk about Coriolis forces, and we'd go into geostatic winds. I'm going to skip most of that this time, and just really give you the basics so that hopefully you can understand enough to that we can move on with modeling. But anyway, recognizing that wind is the basic element, and one of the things to think about is wind isn't constant. Think about you're out going for a walk. You're walking across campus. There isn't this constant wind. It spurts, okay? You may have small gusts, and then all of a sudden you've got this much larger gust, this much larger mass of air that is moving. This contributes to transport of heat, contributes to transport of pollutants. One of the things to recognize is that winds are always named from the direction in which they blow. So this from is important. They're always from northerly winds, blow from the north towards the south. So a northerly wind blows from the north to the south. Westerly wind would blow from the west to the east. We also talk about prevailing winds. This is the predominant wind direction. So it's not, doesn't mean that there isn't, for instance, if it's the prevailing wind direction is a westerly, doesn't mean that there aren't winds that can move from the east, but it means that the predominant direction is from the west. We also talk about eddies. So you've got all these surface variations, okay? As I mentioned, results in friction. These change the direction of the wind, caused the irregularity, and you start to get kind of what we refer to as eddies, okay? This irregular pattern of the wind. So how does this affect air transport? Let's look at this situation here. Okay, these are two images that I took from the parking lot outside the engineering building on 2 different days. Happened to be a few years ago, but it doesn't really matter. Both one in late February, one in early March, so about a week apart. Big difference, look at the temperature. We have -2 degrees. We have about 17 degrees, so both pretty cold, but February colder than March. Air pressure was fairly similar. Humidity was quite different. And in one case, what we have is referred to as a relative humidity of 100%, in the other case, 72. So let's look at this effects of relative humidity, or this parameter, relative humidity, a little more closely. So relative humidity is defined as it's really the water content in the air divided by the saturation water content, or the humidity divided by the saturation humidity. So we can also represent that as the mole fraction of water times the total pressure divided by the vapor pressure of pure water. Now in the atmosphere, we talked about this before, that we have about 78% nitrogen, about 21% oxygen, about 1% argon, and other trace gases. These are relative constant, or constant over time and space. On the other hand, moisture content is highly variable. Typically, rain is about 1.15 mole percent. That can also be volume percent, as we learned earlier in the semester. But let's think about this in terms of what does this really mean. So if we have a temperature of 50 degrees Fahrenheit and a relative humidity of 50%, at that temperature, we would have a saturation water pressure of 92.2 torr. Okay. Therefore, we have a water content. So what we want is the water content. Call that water content. That's equal to this 0.5 times the 92.2, and that is equal to 46.1. So that's the actual partial pressure of the water, corresponds to the water content. So it would be in pressure, but we can also, pressure is related to the amount of water. What we're really looking at right now is the comparison. If we look at 70 degrees, same relative humidity. So we're going to keep this constant. Here, the saturation water pressure is 233 torr. So the water content, again, is 0.5 times 233, and that would be 116. So you've got much more water in the air, same relative humidity, much more water in the air at 70 degrees than you do at 50 degrees. If we temperature is at 90 degrees, now the partial pressure of, or the saturation pressure of water is 525 torr. So now We're going to multiply that 0.5, same relative humidity. That is now 267.5. So notice, you can see here, it increases from 46 to 116 to 265, 267, sorry. What does that tell you? Well, if you can kind of think about it, you're out exercising on a day where the temperature is 50 degrees. It's a comfortable day. It's a nice day to go for a run. At least I think so. You go out and when it's 90 degrees and you're out there and you're like, oh my God, this is just a horrible day for a run. At least that's my feeling. It's why, because of the moisture content in the air. The moisture content in the air actually makes it more difficult to exercise. It's more uncomfortable. That moisture content is going to play a role in what we're looking, how these chemicals are transported in the atmosphere. Now, we can look at the effect of temperature and humidity. And basically, this is just looking at we've got the density. So the change in density, it's just dP over P, okay? So it's, and that's because, remember, density is equal to N over V, which is equal to P over RT. So 1 over density is equal to RT over P. And then if we start taking differentials, now we have the differential here. So we're looking at the change as a function of temperature. So we've got differential here. We're going to take the differential here. R is a constant. We're going to assume pressure is constant. So we're leaving that as a constant, dt. So that is this d1 over p. So we're taking the change in density. Okay. Yes. And that here shows you right here, this is what we really want, is that the change in density, okay, function of t is equal to about 3.4 times 10 to the minus 3 inverse t. And here we have a similar expression, but we're looking at it in terms of relative humidity. And basically what this shows you is that you have to have about a 40% increase in relative humidity in order to produce the same effect as 1 degree C. Okay, so 40% change in relative humidity results in the same effect on air density as a temperature change of 1 degree C. That tells you that temperature is what's controlling air density, which is controlling air movement. And that's what's controlling transport. I'm just going to go back because, oh, I'm sorry. The question is, what is NC? That's supposed to be WC. It's not a water closet. It's actually the water content. So it's the water content in the air. So that's how much water is actually in the air. So kind of if you took the same amount of volume of air, you could squeeze out a lot more water at 90 degrees than you could at 50. So hopefully that helps. Okay, so now let's look at what we ultimately really want to do is we want to start looking at again, how does air move? Or how do pollutants move? So the basic equation of fluid statics is right here. Seen it in 321, seen it in other classes. Change in pressure as a function of z elevation is equal to minus rho density times gravitational acceleration. Now, density is just mass over volume. So what I've done is I've just derived the equation here. So mass is equal to the number of moles times the molar mass of the molecular weight. Divide that by volume. Volume, we've just used, again, PV equals nRT. Volume is equal, 1 over volume is equal to P over nRT. So N cancels. And we have that density is equal to the molar mass times P divided by RT. So we can substitute, so we're just substituting in here for the density, and we have this expression here. Okay? So that says that the change in pressure with elevation is inversely proportional to temperature. Now, what we need to think about, and this is as we kind of move into looking at the stability of air, is really what we're looking at. We're looking at air movement. We have this equation right here. Okay. This is going to be the predominant equation that we're essentially looking at. And we have this parcel of air. So think of the parcel of air as a balloon. Okay. We are going to assume that the change in heat between the balloon and the surroundings is equal to 0. So we have no heat transferred between the surroundings and the balloon. We're also going to assume that the balloon is able to stretch so that we have no work. So there's no work done on the surrounding. Now, what happens? As my balloon, so I'm going to do it here, if I can. Okay, so here's my balloon. Let's draw a balloon. Can't draw a balloon. There's my balloon. It's a really bad balloon, I apologize. But there's a balloon, okay? It's a helium balloon. The balloon rises. Okay, what's going to happen? As that balloon rises, so as it rises, what happens to the pressure? The pressure decreases. So as the pressure decreases, my balloon is going to get bigger. So the volume in the balloon increases. So my balloon expands, the volume increases, and now what happens to temperature? Temperature is going to decrease. Yep, I can make the pen smaller, I think. My son made it bigger before because he said it wasn't small enough. So if I can figure out how to do that, I will. Okay. Let me know if that's a problem. Let me know, and we'll adjust. Okay. So what we're looking at right now, okay? This process here, this process of the fact that no heat is exchanged between the air parcel and the rest of the atmosphere means that we have an adiabatic process. So that's what an adiabatic process means. No heat is transferred between the balloon, inside of that balloon, that inside of the parcel, and the surroundings. Now, We can also assume that the process is reversible. If we take this balloon, we've got it on a tether, we bring the balloon back down again. Okay. So as we bring the balloon back down, what's going to happen? I'm going to switch and see if we can do this. Switch to color. Okay. And let's pick red. So what's going to happen? If I can make this work. Okay, so now we're going to bring the balloon down. What happens? As we bring the balloon down, now the pressure increases. Okay. Temperature is also going to increase and the volume decreases. So if we bring it back to where we started again, ideally it should end up exactly where we started. Same volume, same temperature. And that's what this is just trying to show here. Okay. So we've got a parcel, starts out at 30 degrees here. So here's our parcel. As we allow this to rise, the pressure decreases as it rises. So as it's rising, pressure decreases. You can see the temperature decreases and it's expanding. So it says as it's expanding, it's cooling. We bring it back down again. It's going to warm and it's going to compress. Okay. Again, all of this happens. We're assuming that this is an adiabatic process. So what we talk about is we talk about an adiabatic lapse rate. So that's the rate of change of the parcel as it rises or sinks with altitude. And it's as a result of adiabatic expansion or compression so I'm just going to switch. Okay. So I can go back here to black. So we're talking here, if it's rising, it's expanding. And then if it's sinking, it's going to contract. Now, we'll talk about two different adiabatic lapse rates. The first one we're going to talk about is dry. So we're assuming that the air is unsaturated and we have no condensation. So there's no condensation. If that's the case, then the rate of change with elevation is about 10 degrees, and this is actually a decrease, so it's actually a negative. So it's decreasing 10 degrees C for every kilometer that parcel rises. Okay, and this rate is independent of temperature. Okay, so it's independent of the ambient temperature. Then we also talk about the environmental lapse rate, and that's the actual rate. So if I went outside and I could measure the temperature of the air at the ground surface, and then I measure the temperature of the air as it moves, okay? I let that balloon rise. I measure the temperature at 500 meters. I measure it at 1,000 meters, 1,500 meters, etc. So let's say I've got my balloon. So I've got a weather balloon, okay? And I'm going to measure the temperature. And we'll measure it at ground surface. And let's say we'll measure it at, we'll measure it at 1,000 meters. We'll measure it at 500 meters above ground surface, 1,000, etc. Okay, and so I measure that. plot that, that's going to give me the environmental lapse rate. We're going to use really simple projections of the environmental lapse rate. It's actually much more complicated, but that's beyond what we will do here. So think about this here. So what we want to do is we want to look at, or we want to be able to determine how that pollutant is going to move. So what you see here, okay, is a depiction of the dry adiabatic lapse rate. So 10 degrees decrease for every 1,000 meters. So we've got 30 right here, okay, 20 right here, be 10 degrees here, and 0 degrees at 3,000 meters, sorry. So, and you can see that here. So this here corresponds to the dry adiabatic lapse rate. So we're looking at our parcel, okay, and we're representing that here. So think about this as this balloon that we're letting rise. Now, this is what we actually measure. Sometimes. So this is, temperature is the actual temperature. This is what we go out and we measure. And then we start at the same thing. We start at 30, okay? And at 1,000, it's 26. At 2,000, it's 22. And it's 18 at 3,000. So now what are we doing? We're looking at, we're comparing this. This is our balloon. What's going to happen? This balloon here is cooler than the atmosphere. It is cooler than the atmosphere. So if it's cooler, it's heavier, it's more dense. And what do you think it wants to do? Sink back down. Okay. So in this case, I'm going to think about this as a pollutant. Okay. It's going to want to sink back down. It's going to stay close to the ground surface. Think about what we talked about at the very beginning in terms of the thermal inversions, in terms of these air pollution incidents. Our pollutant wants to stay close to the surface. Now, the other thing we need to think about is we don't always have a situation where that air is unsaturated. So we have water. So when water evaporates, heat is absorbed. When water condenses, heat is released. So think about what's happening with this balloon. So as this parcel of air rises, so we've got this parcel of air, here's my parcel of air, okay, it's rising. And it's cooling. So what happens? Go back to think about the relative humidity. Okay, here we have the same amount of water. So what's going to happen? The relative humidity increases because the water has no place to go. It's got to stay in the balloon. So that means the relative humidity increases, the air becomes saturated, the water condenses, that releases condensation, releases latent heat, and now the air is warmed. What this means is that we're going to talk about both, we talked about a dry adiabatic lapse rate. We also talk about a moist adiabatic lapse rate. That moist adiabatic lapse rate is going to be greater, less negative than the dry adiabatic lapse rate because of the heat that's given off. So the moist adiabatic lapse rate, okay, because of this latent heat, what happens is it's cooling, the mass of air is cooling due to expansion, but the water is condensing. That gives off heat. Cooling wins, basically, it's still going to cool, but the lapse rate is less than that for dry air. Remember, the dry adiabatic lapse rate is 10 degrees C per kilometer. For moist or wet adiabatic lapse rate, it's about 6.5 degrees per kilometer. It does depend on temperature and moisture. We're not going to worry about that dependence. We'll stick with 6.5 degrees Celsius per kilometer. So now, here what we have is we have a situation, think about it, where we have fog on ground surface. You wake up in the morning and you've got this foggy day. Why do you have fog? Because of the moisture. Moisture is condensing in the air. And that's what produces the fog. So think about this as it's a colder day, you've got fog. So we're going to use the moist adiabatic lapse rate. This image uses 6.5, it's somewhere in that range. We'll use right here, because of the image, we'll use 6. And you can see here, so now we're going to use and why doesn't this work? I'm not quite sure. Why is this not writing? Anyway, this is, forgive me. This is so we've got the moist adiabatic lapse rate here. Okay, it's decreasing at 6 degrees per 1,000 kilometers. So it goes from 30 to 24 to 18 to 12. Okay. Environmental conditions were the exact same as before. 30, 26, 22, 18. Again, what do you see? That and I'm not quite sure why this is not doing this. But what we see here is that in all cases, and the temperature is less, it's going to be more dense. So because it's more dense, it's going to want to sink. So again, what this is going to do is we're talking about a stable atmosphere. So we're talking about conditions where if we're looking at a pollutant, is going to want to stay close to the ground surface. So we just have the comparison here, okay? So in this case, we have the dry adiabatic lapse rate. In this case, we have the moist adiabatic lapse rate. But in both cases here, the parcel temperature of the parcel is less than that of the surrounding air. So it's going to be more dense, and it's going to want to sink. Okay, so what we have in this case is an atmosphere that we refer to as stable. And so if the parcel is colder than the surrounding, it wants to sink. If it's warmer, it wants to rise. If it wants to rise, then what we have is an unstable atmosphere. In this case, we have a stable atmosphere. And that's essentially what we're looking at right here. Now, in this case, we actually have a situation, we have clouds that form. So we have clouds at, not quite sure why some of these slides will let me draw and some will not. I'll figure that one out. But what we see here is, and actually what I'm going to do, I think, is stop here. Between now and Wednesday, what I want you to do is take a look at this. Okay, so what we have is we have clouds forming at 2,000 meters. So that's why we switch from the dry adiabatic lapse rate, and at this point we're going to use the wet adiabatic lapse rate. And here is the atmospheric temperature. Now, in both cases, what we're doing is we start at the same temperature. Okay, so what I want you to do is take a look at this and compare this parcel right here, temperature of the parcel, with the atmospheric temperature. So the actual temperature. And see if you can convince yourself that this is, in fact, a situation where you have what we call absolute stability, that it's at all conditions. And then in this situation, look at this one. Okay? Look at these two. This one, it's absolute instability. Again, we have clouds forming at 2,000 meters. So we're going to use the wet adiabatic lapse rate after, at elevations greater than 2,000. We'll use the dry below that. We've got the environmental conditions right there. And look at these and see if you can convince yourself that this is absolute instability, okay? That our pollutant wants to rise. So take a look at that. In the last couple minutes, are there any other questions? Yes, no? No questions? Just a reminder, as I mentioned in the beginning, and I'm going to switch back to the beginning. As I mentioned, I've posted a revised syllabus. There's no changes to the grading scheme for the first half of the semester. I have changed the grading scheme for the second half. I'm eliminating exams 2 or 3, making homework worth 20%. Project is going to be worth 42%, and participation is slightly different at 10.5%. So basically, think about the second half, okay, or think about this in points. At 100 points, homework here is worth 20 points. Homework was worth 7.5. And that first half and the first exam is worth 20%. You've also got the extra credit posted. I've posted numerous videos. They're online seminars that you can watch. And then also a reminder that homework is due on Wednesday, both for greenhouse gases and air pollution regs. So if there's no other questions,
Dr. Maston.
yeah.
Could you explain again the difference in the last two diagrams about how you defined stable and unstable?
Yeah, sure.
Between them? Thank you.
I can do that, and then I'll try and answer the last question. Okay. Okay. These two diagrams, or the other two? The previous.
Yes, these diagrams.
Okay. So basically here, what you see, we started in this case at 20 degrees. Okay. We're gonna first do your dry adiabatic lapse rate. Think about that first. So the dry adiabatic lapse rate is 10 degrees C per 1,000 meters. So at 1,000 meters, the temperature is 10 degrees. At 2000, it's going to drop another 10 degrees, so it's 0. And I don't, okay, so that's right there. Now, we've got clouds forming right at 2000 meters. So now the temperature is only going to drop, let's just use 6 because it's a little bit easier. Okay, so now it's going to drop from 0, it's going to drop 6 degrees. So it's -6 degrees. So we've got this right here. It's going to drop another 6 degrees here, and it drops another 6 degrees here. So, so temperature's dropping. So you can see here, this is our atmospheric lapse rate, or dry adiabatic lapse rate. So we can see this temperature. This here is what I would measure. So if I went out and I measured the air temperature, okay, it's 15 degrees 10. So this is the actual measurement, what I'm measuring. And what you see here is that in all cases, okay, my balloon, my parcel's temperature is less than the surrounding. So what happens? It's more dense. I apologize. So it's more dense, and now it's going to tend to want to sink. So that's why it's stable. And then if we look here, the question, so the issue here is now, let's look here, we start, it's 40 degrees here. So we're going to do the exact same thing. So look at the dry adiabatic. This is our parcel. So it's here, if we start at 40, we're now at 30, we're at 20. Now we have clouds forming again here. So now it's going to decrease at 6 degrees, so it's 14 and 8. Now this is my environmental temperature. Notice in all cases it's greater. So if it's greater, it's less dense. So it's warmer, it's less dense, and now my parcel wants to rise. So that's why it's unstable. Okay? Because now my parcel, now think of my plume, so here's my smokestack, and now it's going to want to rise, okay? It's going to, my pollutants are going to want to rise versus before, my pollutants are going to want to sink to the surface. So here, if it's stable, and here's my person, so this is unstable. If it's stable, here's my pollutants, and now my person is exposed more to those pollutants. That help?
Yes, thank you.
Okay, any other questions? I know I'm gone over. There is a question about opening up all the notes to print it out at once. I could, except because I didn't teach last year. The last time I taught was 2018, and I'm actually redoing my notes, updating everything. So for that reason, I can't open up the notes ahead of time because I don't have notes for the rest of the semester. Pretty much finishing the notes the day before class. So I apologize that I can't open up the notes ahead of time. It's because I try and make sure that I revise my notes every semester that I teach something. So I'm sorry that I can't do that. Any other questions? Okay, if there's no questions, we'll stop there. And